Okay, so welcome to this lecture. We're going to work on something in this lecture that is not essentially important for this chapter or this module in general, but it's something that's important for next, if you go into level 7 in a slightly different context, something called Laplace transforms. So we've got our little strategy for doing antidifferentiation. The first thing you do is you just look in the tables. Can the thing be done directly? If it's not in the tables, you try a manipulation. That's rewriting what you're working with. If that doesn't work, you can try a W substitution, and if that doesn't work, you can try integration by parts. Now, there are many techniques you can keep on going here, but in this section there's a particular manipulation that we're going to look at. Okay. So it involves inverse sine and inverse tan. Now, in last week's lectures we showed the derivative inverse sine looks like this. Similarly, you can show that the derivative inverse tan looks like this. And using these things, running them backwards, we have these in the table integrals that the antiderivative of this is inverse sine and this one is inverse tan. Okay, so these are in the tables. You can show them directly by differentiating. Okay, so what have we got? So if we look at both of these, we have a squared minus x squared and a squared plus x squared. Now, if there is in addition an x term, there's different things that can happen. But what we're going to do in this one is we're going to, if we have an extra x term, we're going to try and write it as if it's a sum of two squares or a difference of two squares. And in a certain sense, you can always do, I think if I'm correct, you can always do one or the other depending on what's going on. This would be a special manipulation. Okay, so if you have a quadratic with an x squared, that's what quadratic means. That's not a sum or difference of two squares like the ones we just showed. If the x term appears also, you do something called completing the square. Okay, now, so here you've got a quadratic plus or minus x squared, a multiple of x, and a constant. Write it as a sum or difference of squares. Now, if the x squared is plus, it'll be a sum of squares. If the x squared is minus, it'll be a difference of squares. And actually, as I say that, I know that if it's a plus x squared, you mightn't always be able to write it as a sum of squares of this form, but don't worry too much about that. Okay, so let's see how this looks like. So this, now the question is, oh, how do you know when to do it? Well, I suppose what we would say in this module is that this is one of the things we've shown you, like, so be looking out for it. But strictly speaking, it's a technique if you do a lot of antidifferentiation that's in your toolkit. So what completing the square means is we have this x squared plus x plus 5 over 2. What we're going to do is we are going to write this in the form a squared plus x squared, but the x, instead of x, it's going to be x plus b. In the language, if you're going to level 7, this is the x is shifted. Okay, so this is something that you want to do. I'm just going to put this exclamation mark here to kind of give a sense of urgency that this is something that you want to do. You want these two things to be equal. Now, there's various different ways of doing this, but the way that I like doing it is, if I want these to be equal, let me multiply this thing out. So if I carefully multiply it out, I get a squared. Now we'll carefully multiply out x plus b. Now I won't do the full thing, but I'll just show it. It's not as simple anyway as x squared plus b squared, because it's x plus b times x plus b. And what that means is what you get is, and I'm going to write it in a particular form, which isn't ideal, but anyway, a squared. Now how many x's do you get? You get an x by b and a b by x. And of course they're the same, so you've got 2bx. And I've already messed up the thing I didn't want to mess up. But anyway, so I have a squared. And what about b by b? That gives you b squared. I'm just going to throw that there. Sorry, that's a bit messy. But anyway. And then you also have x by x is x squared. I've made a bit of a hames of presenting that, but all I'm basically trying to say is that if I have x plus b times x plus b, I do x by x is x squared plus x by b is same as bx plus bx is bx, and you also have plus b by b, which is plus b squared, which is equal to x squared plus 2bx plus b squared. Okay. Now, I want this to equal this. This does equal this, and this does equal this. So I want these two things to be equal. Now let's compare them. They both have an x squared. That's good. How about the coefficient of x? Now, when I said the coefficient of x, what that means is the number that's multiplying x. Now, the number multiplying x on the right-hand side is 2b. Okay. And the number multiplying x on the left, now you might say there's no number, but that's not quite right. I mean, what does no number mean? If it means 0, it's 0x, but 0x would be 0, so it's not no number, it's not 0. How many x's have you got? Well, 1. It's the same as 1x. So if you're forcing these two to be equal, you want the 2b here to equal the 1 here. And then finally, and this is why you might appreciate why I messed up the way I wrote it, I want the constant over here, which is a squared plus b squared, to be equal to the constant over here. Okay, if I can do that, then I can write x squared plus x plus 5 over 2, in this form. Okay, so let's force these things to be equal. So I want 2b to equal 1. Divide both sides by 2. I get b is equal to 1/2. That's done. And I also want a squared plus b squared to be equal to 5 over 2. Now I've just found out that b is equal to 1/2. So b squared here is 1/2 squared, which is 1/4. I can take the quarter away from both sides and I'll end up with a squared is equal to 9/4. And I do the square root of both sides and I get a is equal to the square root of 9 over 4. Now we should be careful. This has two roots, so it's plus or minus. But what you can do is you can always choose it to be the plus one, so just forget about the plus. And the square root of 9 over 4, either you know what it is or you go to a calculator, you get 3 over 2. So what we've successfully done is we said if we can write this thing as a squared plus x plus b all squared, a has to be 3 over 2 and b has to be 1/2. So we can write x squared plus x plus 5 over 2 equal to a squared, which is 3 over 2 squared, plus x plus b plus x plus 1/2 squared. Doing this for a general ax squared plus bx plus c actually leads to the minus b formula. Okay, so this is what an exam question will look like. Okay, so we're trying to find this antiderivative down here. Now, first thing we do is we look in the tables. Now, something you might see in the tables, and the thing that looks most like this is this thing here, this inverse tan. Okay, and I say, okay, it looks a little bit like that, but you know, it's not that. So the second thing is manipulation. Is there a manipulation of this? Could I possibly write x squared minus 12x plus 41 as a squared plus x plus b all squared? If I could do that, that would be useful. And this is the special manipulation we're looking at. So what we need to do here is complete the square, write x squared minus 12x plus 41 in the form a squared plus x plus b all squared. So what have we got? So we've got x squared minus 12x plus 41 and we want this to equal a squared plus x plus b squared. This is what we want. So what we're going to do is we're going to multiply out the right hand side and then compare the coefficients. So what this means is this will be equal to a squared plus x squared plus 2bx plus b squared if you multiply out carefully. And I'm going to write this in a slightly different way. I'm going to write it in the same way as this just because the other one's a bit messy. So say x squared, so we can compare the x squareds, plus 2bx to compare the x's, and then the constant is a squared plus b squared. Okay, so now let's compare. So what's good is these are, so might just say at this point that I want these two things to be equal. This is equal to this, this is equal to this, so we want these two to be equal, so we kind of force them equal to each other. Next is we look at the coefficient of x on the left. Now if you're a little bit careless, you might say, oh, it's the multiple of x is 12, but actually it's minus 12 because it's x squared plus minus 12. So this is the coefficient of x on the left. And the coefficient of x on the right is 2b. I'm going to do a big sneeze now. It's not coronavirus. It's chewing gum. Sorry about that. Right, and then what's the constant on the left? You've got 41. And the constant on the left, and the constant on the right is a squared plus b squared, and we need these to be equal for this to equal this. So this is called equating coefficients, or I would just call them forcing the two things equal to each other. So I have 2b must equal minus 12. Divide both sides by b. Sorry, that's nonsense. Divide both sides by 2. Because b is multiplied by 2, dividing by 2 will get rid of the multiplied by 2, and minus 12 divided by 2 is minus 6. And now how about a squared plus b squared is equal to 41. We've already shown that b is minus 6, so b squared is minus 6 by minus 6 is equal to 36. And to get a squared on its own, subtract 36 from both sides. 41 minus 36 is 5. And then take the square root of both sides to get a is equal to the square root of 5. Now this has two solutions, plus or minus, but you can show that you can always choose the positive one. If you choose the negative one, if I think you actually, the answer looks different, but it's actually the same. You kind of get a minus minus situation. So what we have is x squared minus 12x plus 41 can be written as a squared, which is root 5, plus x plus b, which is plus minus 6, which is what minus 6 means, squared. Okay, this is where we're at. So we've rewritten, so it's a manipulation. We've completed the square. We've written the x squared minus 12x plus 41 as a sum of two squares. And then see what we can use now is we can use this, which is in the tables. Now, strictly speaking, just to be careful, we should do a little W substitution, because looking at this, it's not exactly like this in the tables. As it happens, if it's 1x plus a constant, if you go to the tables here, it will be okay. If it was a 2x or something like that, it wouldn't be okay. I would advise doing the W substitution. It's good to practice it anyway. So I look at this and I say it's not exactly in the table. It's manipulation. I can't really do any more manipulation, so I need to try a W substitution. So the now at this stage, looking at you kind of need to know what you're doing here. If you're completing the square, you know you're going to do this is the W. But can we look at it the way we've looked at it before? Yes. You could say here's a function x minus 6. Here's a multiple of its derivative 1. X minus 6 is inside something else, the squaring, and Liate kind of gives it as well, although Liate gives many options here. But x minus 6 is what we want. So this I is equal to antiderivative 1 over square root of 5 squared, and we're putting x minus 6 equal to w, so that's w squared. And if you remember from the substitution, you want to write dx in terms of dw as well. So if w is equal to x minus 6, if you want to get a relationship between dw and dx, what you have to do is differentiate w. So you get dw dx equal 1, multiply both sides by dx, which is technically nonsense, but gives you the right answer. Dx is the same as dw. And this is in the tables, because it's of the form 1 over a squared plus x squared x. So it's 1 over a, using the tables, inverse tan x over a, in this case w over a, inverse tan w over a, w over root 5. Okay, and for full marks, the original antiderivative that we've been looking at here has been with respect to x, so we should go back in terms of x as well. So this is x minus 6 divided by root 5, and for full marks we need to do plus c. Okay, so this is a pure kind of easy when you know how question. I think now there's some of you are very strong in this class, but I think you could be a month at this on your own and you wouldn't be able to get it. It's a little bit of know-how. When you go into level 7, this complete the square comes up in a different context and you're kind of more expecting it. I mean, getting an integral like this in the wild, there's other ways that this could go. It mightn't be possible to do this, but this is how this one goes at any rate. Okay, so we'll do another example here. So looking at this one. Now this one, again, we'll go through it. We'll go think about the tables. Okay, we're looking at the tables. You see this thing, right? But it's not in the right form because you got this extra x. So tables is out. Now, the thing here, if you kind of skip manipulation and talk about w substitution, you get into a world of pain. If you do w substitution here, I think you'll end up with something like 1 over square root of w, but there'll be loads of x's lying around. I think something like a 2 minus 2x or something. And when you've got w as an x, the substitution has failed. This is why I say if you try to do this on your own without seeing this, you'd be in trouble. Integration by parts says nothing here. It's this special manipulation called completing the square. So yeah, the other thing in level 7, this x is called shifted. It'll actually be an s, and that's something that'll all be kind of on your mind. Oh, could it be a shifted thing? Could it be the same as this, different context now, but instead of the x plus b? So anyway, this is what we need to do. So we're going to complete the square here, but this one, it's a minus x squared, so this is minus. If it's a plus x squared, this will be plus. It's a minus x squared, it's a minus. So we do 15 plus 2x minus x squared. We want this to be of this form, a squared plus, oh god, what a donkey, minus x plus b all squared. So this is something that we want to happen. Now if you get to here, you've done great work, and there's just one thing that might catch you, just this minus sign. Just be a little bit careful. So this is a squared minus, and I recommend you do all this squaring inside in this bracket maybe. So this is x squared plus 2bx plus b squared if you multiply it carefully. And what we'll do is I'll put all the constants together because the first constant is here. So I get a squared minus b squared. Now let's talk about x's. Minus 2bx. And then finally minus x squared. So just being a little careful with the signs. We want this to equal this. This does equal this, and this does equal this. So I want these two to be equal. Let's compare. They both have a minus x squared. That's good. What about the coefficient of x? The coefficient of x here is 2. That means the multiple of x. And the multiple of x here, now again, be careful with the minus, it's minus 2b. Okay, let's look at constants here on the left. We got 15. And constants on the right, a squared minus b squared. So if we can force both of these things to happen, if we can find the value of a and b that does this, then we're away with it. Okay, so first of all, Now you want to do this one first because you can see, oh, b is going to be -1. Well, let's see it explicitly. So minus 2b, we want this to be equal to 2. So we divide both sides by -2. And we get b is equal to -1. Happy days. And now we go at the other one. Now remember, all the time here you can pause me. I appreciate this is kind of difficult, so it's an excellent video to be pausing me. A squared minus b squared equal to 15. We know that b, now here the signs are at us again, right? B squared is -1 by -1. That's definitely 1. So this is a squared minus 1. You want to get a on its own, you got this -1. The inverse of -1 is adding 1. Do it to both sides. You get a squared is equal to 16. And then you want to do a square root. And it's important to me that you understand that these squares have two solutions, so really it should be plus or minus. In other contexts, like here it doesn't matter if you forget about the minus. In other contexts it's very important. I'm saying you can choose it to be whichever one you want, so let's choose the easy one. If you choose the negative one, it's not wrong, but it's just a bit daft. Square root of 16 is 4. So what I'm going to do on the next page is I'm going to rewrite this antiderivative like this, because this is what we've done. We've achieved a is 4 and the b is -1. So I'm going to rewrite this on the next page. So rewriting that, we get 1 over square root, using this a, which we found to be 4, so it's 4 squared minus x plus b, we found the b to be -1, x minus 1 squared dx. Now if you do try and use the tables from here, I'm going to have to be honest with you and tell you you will get the right answer, but that's only because it's a 1x. If it's anything else, that will lead you down the wrong path. So I recommend doing a little substitution. So the substitution, similar argument as before, we'll play dumb on it, watch the thing. So if you're very good at substitution, you see a function multiple derivative. So the function is x minus 1, its derivative is 1, function multiple derivative, let the w be the x minus 1. Next thing is you look for something inside something else. Now in fairness, I do see all of this inside the square root, so here it's a bit more difficult, but x minus 1 inside the square, that should be it. Then liate, no logs, no inverse trig, no algebraic. Yeah, there's algebraic, but again, you'd be tempted to pick everything in the square root when it's just the x minus 1. So whatever way you want to bake it, the w should be x minus 1. Then what we didn't show on the previous page was you want to write dx in terms of dw. How do you get a relationship between dx and dw? You differentiate w. And then you multiply, which is nonsense, but it gives you the right answer. dw is equal to dx. So we can rewrite this antiderivative as antiderivative 1 over square root 4 squared minus, now this x minus 1 is now w. And the dx is equal to dw. And this is in the tables because this is an inverse sine. Look, 1 over square root. Yeah, if you can't see the pattern, I'm afraid I can't. If you've done all this, you can see the pattern. 1 over square root 4 squared minus w squared. It's just w in terms of x, so it'll be inverse sine w over the a here is 4. And the original question was looking for the antiderivative with respect to x, if I can find it. So we should put our answer in terms of x as well. So put the w back as x minus 1. So you get inverse sine x minus 1 over 4. And then for full marks, you want that plus c. So yeah, if you want to get really good at anti-differentiation integration, there's an absolute zoo of techniques. We're only scratching the surface. The truth of the matter is you'll use software. But if we're just going to be concerned about this module and not look at the big bad world, you're probably going to see one of these in an assessment, and kind of not the rule as such, but what you're thinking is if it's 1 over a square root, it's going to be 1 over a negative quadratic with a minus x squared. That should lead you to look at the formula for inverse sine, which forces you to look at a squared minus x squared, and then, you know, all the manipulation is such that the x is x plus b, and a similar story for the inverse tan.